Mathematics is often motivated by shockingly simple and stupid questions. For example, what are surfaces? How can we compare one surface to another, distinguish them? How would you go from point A to point B on such a surface? In some cases, the answers might seem obvious. Here, for example, the exterior of a cube, a sphere, and a donut, also called a torus, should clearly be considered as surfaces, and we can already start to see distinguishing features. This is fun and all, unless you're a mathematician. Then you want some precise answers and definitions. The field of mathematics that studies these kinds of questions is called differential geometry, and that's what we'll be diving into. I'm planning to do many videos on the subject, going from the basics to some more advanced concepts. Today, we'll be tackling differentiable functions. The main prerequisites for following these videos would be a knowledge of linear algebra and topology of finite-dimensional vector spaces. With this out of the way, we can now begin our journey into the unknown territories of differentiable functions. So, before tackling anything, we'll need some basic definitions, inherited from real analysis. For a function f from an open real interval I to Rn, we define its derivative at point t as the following limit, if it exists, of course. This value is then a vector, and not a real number as in the usual definition. But that's okay. Almost all that we know about real derivatives transfer over to these vector derivatives. We can also define the definite integral of f between a and b, which can be expressed like this. Again, this definition yields a vector, and we have a lot of the same properties as with real-valued integrals. For instance, the fundamental theorem of calculus still holds, and triangle inequality also still holds. So, what is a differentiable function? It's a generalization of the same notion seen in real analysis. Differentiable functions are those which are well approximated, locally, by affine functions. That's what the following definition is trying to convey. Here I use an open set U as the domain of f, because to talk about local properties around A, we need to have neighborhoods where f is defined. That's exactly what's going on in the equation involving the small o notation. If you're not familiar with it, here is what it really means. The linear function L, approximating the change of f at A, is in fact unique, as stated here, and we call it the differential of f at A. Some of you might already know another way to differentiate functions with more than one variable, called the partial derivative. What is the good notion of differentiability to use then? Well, let's first take the definition of a partial derivative along the ith variable. This rewrites more compactly as this. If we now assume that our function f is differentiable, we can then go on with the computation. And get this nice result. So the two notions are indeed related. In fact, they are almost synonym. The differential of f at A is a linear function, and so it has a matrix. We call it the Jacobian matrix of f at A. What we just showed about partial derivatives allows us to describe the whole matrix. Now that we know what we are talking about, maybe some examples will help to see better how differentiating works. Here I wrote down some useful examples of differentiable functions and their differentials. Assume we got ourselves a function f, differentiable on its whole domain. We can then consider the following map, from U to the space of linear maps from RQ to RP. We can work with this df map to uncover more of the behavior of f. We'll call this map the differential of f. The approach is similar to considering the derivative of f in the real case. We can in particular define a notion of regularity stronger than continuous. F will be called CR if its differential is one lower order regular, so CR minus 1. The idea behind it is that a function being CR means we can differentiate it R times and end up with a continuous function. We saw the link between partial derivatives and differentials, and so a natural question would be to rephrase this definition in terms of partial derivatives. It takes the following equivalent form. We see again the idea of partially differentiating f R times and ending up with a continuous function in the end. The k partial derivatives here really means that we first differentiate with respect to xyk, then go up to xy1. Well, in fact, the order in which we differentiate doesn't matter, so that's why we often just use the first form for compact writing. This result, that the order of partial differentiation doesn't matter, is called Schwarz theorem. Here it is in its full form. One very helpful tool for computing differentials is the chain rule, which tells us how to differentiate a composition of differentiable functions. Okay, the next concept we'll tackle are diffeomorphisms. They are the differentiable equivalent of homeomorphisms, maps that preserve the topological properties of spaces. A diffeomorphism preserves even more the differentiability-related properties of spaces. The formal definition is as follows. One funny thing about what we did so far is that the concepts we defined kind of generalize linear algebra to a more general class of spaces and functions. The generalization of a linear map is a differentiable function, so a function with local linear behavior. With this in mind, the natural candidate for generalizing isomorphisms, bijective linear maps, would be diffeomorphisms. And indeed, they got some properties that go this way. The first one is the following. The proof of this proposition is quite easy and goes as follows. First, use the definition of the inverse of f, then differentiate it. But the differential of a linear map is the map itself. Apply the chain rule to compute the left side. Okay, now we got something interesting. If we now do all these steps but with f-1 composed with f instead of f composed with f-1, we get the same equation in reverse, and so the two maps are indeed inverses of each other. So, this proposition tells us that diffeomorphisms behave locally like isomorphisms. But what about the converse? This question will be our main focus for this part of the video, and it is the main result we'll prove. It is called the inverse function theorem. The theorem tells us that a CR function, whose differential is an isomorphism at a point, is a diffeomorphism around that point. In French, we call it the local inversion theorem, and I think the name describes the content of the theorem quite well. Let's now prove this quite powerful result. Okay, so to simplify things a little, we'll assume that the differential of f at A is the identity. This can be achieved by composing by a well-chosen linear map, since we assumed that this differential was an isomorphism. Now, recall our hypothesis. F is a CR function. So, its differential map, df, is then at least continuous. Applying this, we get the following, where we choose to work with the operator norm on the space of linear maps. We can deduce the last line by using the fact that the set of linear isomorphisms is open in the space of linear maps. This is essentially true because of the determinant. Now, recall our goal, proving that f is a diffeomorphism on the neighborhood V of A. Let's first consider the ball of radius r as our first candidate for V. Our goal then reads like this. Okay, so now, if we recall that the differential of f is an isomorphism on the ball, this feels wrong. How can we go from x to z with f behaving as an isomorphism near every point and still get the same value? We encapsulate this with the following trick. We first restrict ourselves to a path between x and z. Then, we make use of the fundamental theorem of calculus to relate differentials and actual function values. The computation leads us to this. Now, if we think about what we noticed before, the differential of f was very close to the identity, so integrating f, or the identity, should result in the same thing, more or less. Let's make this observation precise. We will consider the difference between those two quantities. By some rearranging, triangle inequality, making use of the operator norm definition, using the proximity of the identity to df, we get what we want. Here epsilon is just a very small real number. Returning to what we had, we can now lower bound the norm of this integral by reverse triangle inequality. And here is our contradiction. The first part of our proof is complete. We inverted f on the ball of radius r. Now we want to show that f-1 is CR to make f a diffeomorphism. Showing that seems a bit hard, and CR requires the function to be CR-1, -2, and so on. So we can first try to see why it should be continuous first. But then, on which set is f-1 continuous? We show that it is on the subset of its domain, defined by the image of the ball of radius r/2. We'll again use contradiction. If f-1 isn't continuous at y, then it means we can choose a sequence of points that verify the following. But this sequence lives in the image of the ball of radius r/2, so it can be written as the image of a sequence in this ball. But the closure of this ball is compact, being closed and bounded. We can then extract a converging subsequence from xn. Its limit will be different from x, because we assumed xn didn't converge to x. Now, the continuity of f gives us the following. We then get our contradiction. So f-1 is indeed continuous, but we wanted way more initially. So how can we get there? The following result allows us to finish the proof. I won't prove this one because I think it serves as a nice exercise, making use of all the definitions and properties we already talked about. Anyway, we just proved our function f verifies the two conditions, so the proof of the inverse function theorem is done. Now, let's apply this new result to gain a bit more insight on the correspondence between isomorphisms and diffeomorphisms. The following corollary, also known as the global inversion theorem, gives us some sufficient conditions for a function to be a diffeomorphism, based on its differential and assuming it's already a bijection. Let's prove this result. By the inverse function theorem, the function f is a local diffeomorphism around every point in U. We'll denote by Wx an open neighborhood of x on which this is the case. I now claim f is open, or in other words, the image of an open set by f remains an open set. Indeed, consider an open subset of U, W. We can write it like this. Then, applying f, a bijection, we get the following. So f is indeed open. We deduce that f is a homeomorphism. It is bijective, and because it is open, f-1 is continuous too. We can then apply the lemma discussed in the last proof, and we're done. Now we'll do some concrete applications of local inversion. Polar coordinates are a coordinate system for denoting a point in the plane where the first coordinate r is the distance from the origin, and the second, theta, is the angle the point makes with the horizontal axis. It can be expressed by the following map. We excluded 0 because of the ambiguity it causes with the angles. This coordinate scheme is often used in physics for describing problems with some rotational symmetries. Because it is physics, the problems almost always involve some kind of differential equations or quantities. We would like for this map phi to be at least a local diffeomorphism at every point, so that we know that every differential stuff we do in polar coordinates corresponds to something tangible in the real plane. Fortunately, physics works, and this map is indeed a local diffeomorphism. Phi is indeed differentiable, it is even differentiable infinitely many times, and has the following Jacobian matrix. The determinant of it is then R. So by the inverse function theorem, phi is a local diffeomorphism around every point. So, to wrap up and summarize, we define differentiable functions to be maps whose changes are well approximated by linear ones at every point, and the mapping from a point in the domain of f to its linear approximation at that point was called its differential. A CR map was then a map you could differentiate r times before ending up with a continuous function. We also linked these concepts to partial derivatives and showed some ways to compute differentials, such as the Jacobian matrix and the chain rule. Lastly, we proved the inverse function theorem. If the differential of f is an isomorphism at a point, then f is a diffeomorphism around that point. I always find it useful to make these objects less confusing and scary to try and manipulate them. So here is a little exercise for those who will like it. It is pretty easy and manipulates the basic definitions of differentiable maps. You can also try to prove the lemma using the inverse function theorem, if that's more your taste. Next video, I think I'll be covering coordinate systems on open sets and how those generalize the change of basis from linear algebra, and some geometrical properties of differentiable maps relating to volume preservation.